Okay, so as Debbie says, this is just going to be a fairly quick overview of fire statistics, and it's a sort of a two-part talk. So the first bit will just be generally where we get the stats, what's available in the public domain and elsewhere, and then I will go on with a sort of case study example showing an application of fire stats and sort of going beyond maybe what some people might expect to be possible. So the first bit on availability of fire stats. So in the public domain, there are things such as the statistical bulletin, currently being produced by the Home Office. Before that it was DCLG. And so these will give you a sort of high-level overview, really, of the fire stats for a period of time, either a quarterly or annual bulletin, and they will include sort of fairly sort of standard graphs. So, for example, this one is rather hard to read, but sort of number of fires, total incidents, so non-fires as well, and then this one is fire-related fatalities. So sort of graphs of fairly high level, numbers of fires, numbers of incidents, and so on. And also there are sort of breakdowns like where the fires occurred, so whether they're dwelling fires, other buildings, road vehicles, whatever. So it's all fairly high level stuff. If you need more detailed analysis, then there are occasional publications which break things down into more detail. So an example here of the contents. So looking at things like fatalities in more depth, where they occurred and why. But again, you're sort of restricted really to what the Home Office decide to publish here. So while it's useful, there are sometimes it raises questions that this particular document can't answer. I mean, there's potentially an almost infinite number of questions that you could ask, and only a limited number of pages that you can publish. So, but again, sort of fairly examples of the types of statistics that are presented in these types of publications, sort of fairly high level. Also in the public domain, you can get the spreadsheet tables that were underlying these publications, and again there's an opportunity to sort of therefore dig a little bit more deeply and also do analyses from that spreadsheet data that wasn't actually included in the publication. So this is useful things. So I've given an example here. These are a list of the various sort of high-level topics that you could get. So things like incidents attended, dwelling fires attended, and so on. And then this one here, fatalities and casualties, and then there's further breakdown of about 8 or so different spreadsheets. And just an example, which you won't be able to read, but just to give an idea of the layout of each of these spreadsheets. So there's an introductory tab which tells you what's in the spreadsheet. And then you've got the spreadsheet tables themselves, which are sort of presenting pivot tables of data, and also you can go further into the depths. And so here you've got one row is one fire record, and it will give you sort of details. So this is for fatalities, for instance. So it tells you the year it occurred, what the source of ignition was, where the fire started, and where the victim was found, so whether they're in the room of origin or somewhere else. And so this then allows you to do more detailed analysis than is possible just from reading the publications. If you need to go deeper than that, then you can access the full range of fire statistics from the incident recording system. So the sort of table the contents and all the questions and so on are available in the document online. And okay, so the contents sort of shot through rather quickly there, but there's about 5 pages of contents, over 100 different questions, so a lot of detail is available on each fire, and clearly this is far more than can easily be published. So if you do have a need to get into the fire statistics in detail, then the route is to sort of make a request to the Home Office and explain what you're trying to do and why, and then hopefully they will give you the subset of data that you need. Another fairly recent development in the Home Office is they've started to publish incident level data from the IRS. Now, it's not obviously the complete data set, but they are sort of publishing useful bits from it. And so I've put up a web link here, so if the slides are circulated, then you'll be able to find it. Otherwise, just Google fire statistics and you should get there. So the current level of data sets are these, and so again there's sort of a breakdown, and some of these are really quite large, so the geographical breakdown, for instance, of where each fire occurred, 30 megabytes nearly, so that's every incident for the last 5 or 6 years maybe. So there's a lot of data available there, and sometimes the issue is to sort of tie that in with maybe other data sets in order to extract further information. Okay, so that's just a very quick overview of what's out there, and I've not dealt with other sources of fire statistics. For example, the insurers have their own databases and so on, but what I've just concentrated on is the government fire stats. So what I'll do now is just present a brief application of some fire statistics and how they might be used as part of a wider project, and possibly used in ways that might not be expected. So the issue for this particular project, there was an application intended for combustible material, tire crumb material, and to use to line sort of road cuttings. So the attraction of this material is its acoustical properties. But the drawback is that it's potentially combustible. So the concern is if you have a vehicle fire, then as this develops and transmits heat by radiation to this combustible material, there's a possibility that that can also catch fire. And so the amount of radiation that will fall on the combustible material depends on how much separation you can put between the original fire source and the target material. So the issue here is how can we estimate the risk that the fire will spread? So we define the risk in the sort of conventional terms, frequency times consequence. Here we're really concentrating on the fire frequency, so we need to ask how often do vehicle fires occur, then how quickly can the fire and rescue services attend, how large will the fire size be when they get there, and how quickly the combustible material will ignite, given the size of the fire and the incident radiation upon it. And so we've, for the purposes of this project, defined the consequence that if the time for ignition of the combustible lining material is less than the arrival time of the fire brigade from call to arrival, then the fire is considered to spread. Otherwise, if not, then once the fire brigade arrive, they have an opportunity to get the fire under control and hopefully prevent spread to this combustible material. So looking then at the transport stats from the area where this material was intended to be used, the trunk roads in 4 different regions, the data collected by the trunk road operating authorities over a different period in each region. So we need to work out the average interval, and then from that the number of fires per year. So this is the data, and as you can see, the regions sort of vary quite a lot in the intervals between them. But overall, for all 4 regions, the estimate is around about 50 vehicle fires a year. Further breakdown by the types of vehicles involved. So surprisingly, there's quite a lot of HGV fires and also quite a lot of fires that weren't specified, not actually that many car fires. And so this was Transport Authority stats. If we looked at national UK stats, so I had to go back a bit in time to get data here. So preceding the IRS, there was what was known as the FDR1 forms. The reason we had to go back for this particular project was we needed to know where the vehicle fires occurred in terms of what sort of road they were on, whether the engine was running and so on, to try and get a subset that was representative of vehicle fires in this particular application. The IRS unfortunately doesn't have the details on what road it occurs on, or at least not in an easy form to get at. So we're looking then at the FDR1 fire stats, and we're also looking at the area of fire damage, which we can then relate to the heat release rate of the fire. Generally around about 0.5 megawatt per square metre is typical for many fires, possibly as high as 1 megawatt per square metre. So we have 2 different sources here, and one thing that we can see is the proportions of fires are rather different from the FDR1 data and the regional data. Even though in theory they're looking at the same thing, accidental fires occurring on a road or dual carriageways and motorways. So if you included the unspecified fires, if one assumed that they were all cars, then you might get that up to around about 45%, but still there's a bit of discrepancy. So whether it's a matter of sort of historical differences or not really sure. Another thing to note as well, a discrepancy by roughly a factor of 3 in the total number of fires for the per year. This may be because if these regions here, if they're only restricted to a certain number of roads, not all roads, this might explain this discrepancy. So we haven't looked at this in great detail, but I've just put that up to flag the issues of trying to compare different databases. Even when you think you're comparing like with like, you aren't always. So there are always issues to look at here. As a brief aside, an estimate of the heat release rate from vehicle fires based on the area of fire damage. What's interesting here is, although the vehicles may be very different sizes, anything between a motorbike and a tanker, well, okay, the motorbike's only small, but all these other ones are roughly the same amount of area damaged on average, and so the average fire size actually doesn't depend that strongly on what the vehicle type is. So just looking then at fire area, this is, and converting that to heat release rate on the basis of 0.5 megawatt per square metre. This gives you the probability distribution of fire size, and again you can see that most of these fires are generally rather small, so that's up to about 1 square metre in area, that's up to 2, and then there are larger fires of course, but they are relatively rare. Now, one of the considerations for the risk assessment is the arrival time of the fire brigades. This is the distribution of the arrival time after the call, linked to the subset of fires of interest. And we see that they're arriving typically 10 minutes or so after call. So that is the length of time that the fire will be burning and radiating onto the target material. What is also slightly interesting is that there does seem to be a little bit of a relationship, maybe just by chance, or it may be a causal relationship, that the arrival time does seem to be a little bit shorter for larger fires, though not surprisingly then the amount of time between arrival and control is larger for larger fires. It obviously takes some more time to bring it under control. So just in case that this relationship is relevant, for the purposes of estimating the fire size on arrival, then what I've done is not treat the two things as independent but as dependent variables. So the fire size governs the arrival time. So the next thing to do is to work out what the radiation is going to be on the target. So I've made simplifying assumptions on the geometry of the situation. So I've assumed a cylindrical flame. The reason for doing that is that there are then analytical expressions that will allow you to estimate the radiation incident on the target. So by symmetry, then, if you work out your target point as sort of opposite the halfway point up here, then that will be the place of peak radiant intensity. So some physics now. You will not be tested on this afterwards, so don't panic. But yeah, so you have this rather complicated looking expression to calculate the radiant intensity. That's actually from here to here, so you have to then flip the thing around to work out the radiation from here to here. And then once you've done that, you can then work out the actual radiant intensity. We've also assumed that 35% of the total heat release rate of the fire is actually radiated and the rest is in the form of convected heat. So that then allows us to work out the radiant intensity at the target. And then the next piece of the jigsaw is time to ignition. So we're using this expression here, which depends on various constants, which are material properties, and we actually measured these from the samples of material that we were testing. So the time to ignition then depends on these material properties, the auto-ignition temperature of the material, the air temperature, and then the incident radiation flux. The ignition temperature, the auto-ignition temperature, was something that seemed to be rather variable, anywhere between 200 and 500 degrees. So we represented that by a random variable. And so the overall process then was to run a Monte Carlo simulation of the process of fire spread or not from the burning car. So it was a question of sampling from many times from the actual underlying statistics, a particular fire size and fire brigade arrival time, and then for a given fixed separation between the fire and the target material, we calculated the radiant intensity on it, the ignition time, and worked out whether or not spread would occur based on our criterion that ignition time less than arrival time. And that then gives rise to this graph here. So we have two ranges of points. One is when the heat release rate is 0.5 megawatt per square metre, and then another sensitivity analysis when it's 1 megawatt per square metre. So you can see it falls off fairly rapidly with distance, and when you're at sort of around about 4 to 6 metres separation, then you're probably only getting about 10% of vehicle fires that would transmit to the target material. So then pulling all of this together and trying to assess what the risk would be, we assume that the probability of fire is proportional to the total sort of distance driven and the number of vehicles, and from various sources of data, this rate of fire is around about sort of 3 to 10 fires per 10 to the 8 vehicle kilometres. So fortunately not that frequent. So here's an example then. If the annualised daily traffic is 10,000 vehicles a day along a stretch of road, then a 1 kilometre stretch would expect to have this number of fires per year, which is around about one fire every 3 to 10 years. And then if a fraction spreads to the combustible material, then obviously that's a reduced number of spreading fires per year. So if we know what constitutes an acceptable risk in terms of how many fires per year or the interval between spread fires, then that would then enable us to look back at the graph of spread probability versus distance and then say, okay, this is what the separation distance needs to be. So, just to summarise the talk then, we can use fire statistics in a wide range of different applications, and sometimes it can be quite involved, as with this particular example, using the fire stats as the basis for Monte Carlo simulations of physical processes to work out probabilities of things happening that you can't get directly from the stats. So fire statistical analysis can be just one component of a larger project. So in this case, we were looking at the whole properties of these tyre crumb materials, and so the fire stats was a small but important part of that project. Our clients for this sort of work, a mixture of government and industry. Some of the statistics that we need are available in the public domain, but for more detailed analysis, then we would rely on the Home Office being able to provide us with extracts from the IRS databases when we need more detail. Okay, thank you very much.